All right, so welcome back to this YouTube channel. So in this video, we are going to do. So we have completed object detection and image classification, like in the previous series, and I'm just going to um, come back to this series to explain you to just go through some actually go through a new research paper, right? Not a new research paper for us. It's a new technique. So what this technique is, it's actually optical character recognition to be able to build computer systems that are able to use this RNN and CNN combined architectures. You know, let's say using LSTMs and CNNs combined architecture to actually read. So let's say we have this let's say you have this sentence, right? For a neural network to actually identify different parts of the sentence and actually able to read, not actually reading, but you know identifying certain characters. We can just use a multi-class classification model to be able to give some sequence of matrices, let's say, of either can be the pixels of the actual image or the outputs of the convoluted output. You just input these convoluted values into and neural network and get the characters, right? So that is the idea of optical character recognition. And after we finish this paper, we will not be like reading everything. Though we have only one important part, that is actually the meat of the whole paper. We'll go through that. After we completed this paper, we are going to use this model, use this architecture of optical character recognition to actually solve a problem, to actually do some project. I have put the link of this project in the description, so make sure to check that out. It's not a it's fairly easy project, but we'll be able to at least learn something. I just want to, we should learn to read and research, read and implement research paper. So that is the reason of this video. So first we'll just look at the name of this paper. It is end-to-end trainable neural network for image-based sequence recognition and the application to gene text recognition. So yeah, the name can be quite daunting, but we'll just go through it. So these people here have developed this paper, this paper. So as I've told you, the idea is to use this image. So let's say we have this image of let's say text. So let's say I have an image in which I have, let's say a text name. Let's say there is some text in that image. So we have image that is filled with text. Let's say every pixel of part of that text, like the major part of the text is actually or image is actually text. So let's say this is the image, and state is written on that. Let's say we have this image, state image. So what is the input is? We want this input to be input of this neural network. First, we'll just think of this as just a black box, right? And then we're going to finally get the output as state, the actual value. You might think, when you first listen to this problem, you might think it is fairly simple now that we have already gone through CNNs and all that. But there is some types of, there is a little complication in this thing. So the thing is, we don't know which set of pixels or which part of this image contains the image, right? So which part of this image actually contains the text or letter, let's say. So that is the problem of this uh, task, let's say. So that is why we solve this using this specific architecture. So there are specific many number of architectures, but I'm just going with the simple one, right? So for, let's say we have this image. I'm just going to go through the architecture. This diagram here is like the meat of this paper. The whole I think the whole concept or the whole idea is in this diagram. So let's say we have this image, which is and make sure to listen that the whole image is contained of text. So they make sure that the full image contains text, because we are going to develop a multi-class classification model. So we want to make sure that all the class, like majority of this image contains the text. So we are just going to pass through that through a simple convolutional layer, and then we are going. I think we are using a ReLU here. We're just going to do some convolution layer. Let's say we have some convolutional layers with some kernels. We'll apply these kernels and we'll do matrix multiplications, and we'll update this kernel value. So this is just an architecture. So we are going to do some convolution operations with some kernels, and then after uh, we have performed this convolution operation, we will have a specific number of feature maps. So where, let's say we have at the output layer, let's say we have 32 kernels, then we are going to have 32 feature maps that are going to be generated. So, and then what we are going to do is, let's say we'll get a matrix of, let's say, shape of 32 by 32. Let's say we'll get a matrix with the shape of 32 by 32, and what we'll do is, let's say at every ith index. So let's say we have this ith index, the number I, right? So we're going to have one index, and then so let's say the first index of the feature map, in the first index of the second feature map, the first index of the third feature map. For all these 32 feature maps, we are going to get this first feature maps, and then we are going to right. So we are going to do that. We are going to get the feature maps, the ith number of feature maps. So we'll get a vector, right? So after we have got a vector of this image, so I'm just going to repeat that again. Make sure you understand what's happening. So when you give that image, we'll perform CNNs and we'll identify important parts. And then after we have identified important parts, and after we have some feature maps that are generated by this CNNs, we are going to get this ith index. So we are just going to get ith value of every feature map, and then we are going to have sequential data. So essentially, we are converting this CNN or image. So we are going to convert this image into a sequential data, such that we could find relations in terms of sequence, right? In terms of left to right, and following sequences. That is the idea. You'll get like you'll get select. So let's say this image is a convoluted image. So let's say this is a 3D image. By the way, we have many number of feature maps. So we are going to get the ith index, and then we are going to pass to that as a sequence, right? So that is the idea. And then after that, yeah, we will pass that to an LSTM, bidirectional LSTM. I'll tell you about a bidirectional in the next video. What is bidirectional LSTM, right? So we are going to have an LSTM, right? And then we are going to have, for each feature map, for each index, we are going to predict if there is a word in that specific frame. And after that, after we have predicted the per frame prediction, so every frame is going to predict whether there is a letter in that particular frame, and what that letter is. So we are going to get output like this, and then we are going to get the finally, we are going to use some algorithms to get this final output, which is actually state. So that is the fairly simple architecture, right? So like, yeah, so hope you understand what's going on. So you can just read this. So this is a line that you should probably read. So this actually confused me. So when I was learning this, when I was reading this paper, this confused me that how can we input this feature maps into, how can we convert these feature maps into some sequential data. So this is the idea. We'll just get the ith feature vector. So we'll just get the ith feature vector in the concatenation of these ith columns of all the maps. So we'll essentially get the ith feature vector, and then we are going to pass that through an LSTM such that sequential features are actually found by this network. That is the idea of this neural network. So first, let's look at this model implementation. Not actually very useful. I have figured out that I can train like this model. So I figured out there is a better model. So you could either run this. Actually, this is just implementation. This is just an implementation, right? So as you can see here, the model, we have some CNNs, right? And then we'll reshape this CNNs, and then we'll pass through that to a dense layer, and then we'll give that to a LSTM layer, a 256 units, as you can see. And then after doing some LSTM layers, after finding some sequential features, we'll finally do dense layer with we'll do multi-class classification here, right? So we'll do number of classes. For each class, we are going to predict an output, how probable is that feature or is that input with respect to each class. So this is the implementation. You can just go look at, have a look at it. Like, uh, but still I figured out that there is a better there is a better pre-trained library. So that there is, I think there is a better pre-trained library that can do optical character recognition. So I have in this implementation of this automatic now number plate recognition, I have used that library. So let's go through this code. This is actually fairly simple. We're just doing automatic number plate recognition. So the idea is, to recognize like the numbers. Let's say we have an image of a car, you know, and there's going to be the number plate, right? The one in the front or back. I think it's a white plate, and then some numbers are written on it. So our problem, our task is to read that numbers in that number plate. So for that we do have a little challenge. So what is the challenge is, for performing optical character recognition, you want the whole image to contain the text. So like if you look at the image of a car, like maximum image of that like the maximum part of that image is that of the car, and then the text is actually very small. So the optical recognition model might not be able to find the text. For solving that problem, you might have guessed it, we will use the YOLO algorithm. We'll use object detection algorithm. So first we'll do some pre-processing, right? Wait a minute. So we'll perform object detection model. So we'll perform object detection. I'll go through this code for you, right? So we'll perform object detection. We will use YOLO V5 algorithm, and then we're going to like actually locate that text box or number plate. And then after that, after we have extracted that location of coordinates, we are going to get that image, and then we are going to send that image through a optical character recognition model, pre-trained or a pre-trained optical character recognition model, and then we are going to finally get this output. So I'm just going to run this. I'm just going to show you what is going to happen. Right. So we'll first, like for each image. So first we have to train this object detection model. So we'll have this x min, x max, y min, y max. So the classic object detection, right? And then we'll do some pre-processing. And after that, so yeah, no, I had so before, like, sorry, if you think about this problem, right? If you think about this problem, you don't have to use YOLO V5 if you think about it, right? Because like in normal cases, right, especially in our case, let's say there is only one car. First we assume that there is only one car. So just for simplicity purposes, I think we are assuming that there is only one car. So we are going to get this number plate of only one car. So we can just use a normal classic feed forward neural network. So we are not going to use object detection YOLO. I think I'll do that in the I think I'll use YOLO in the next video, maybe, if you want. Right, so we are just going to run a classic Inception ResNet V2. So Inception ResNet V2 is nothing but just have a word in it. So we'll have Inception, right? So we'll have Inception. We have many sizes of kernels, and then we're also going to have skipped connections, right? Residual connections as of the ResNet. So we are going to have both of this architecture combined. So that is the idea of Inception ResNet. So we are going to use TensorFlow Hub, I think. Yeah, TensorFlow Hub. We are going to have this pre-trained model. So this Inception ResNet V2 is already pre-trained, and all the weights are actually saved. So this model is actually trained on ImageNet, and then we are going to have these weights. We are not going to include top. Include top is nothing but the output layers. We just want the feature vectors of the features that are found by this hugely trained model. And then we are going to set the input shape, and then we are going to first get this output. We are going to flatten it, and we are going to get that through a classic feed forward neural network. We are going to train the model, right? So it's just a fairly simple model, right? So here we are assuming that there is only one car, because if you have two cars as an input, that doesn't really make sense. Which number should you read? should you read? Like if you have two cars, which number plate should you read? That is a problem. I think we can use YOLO, I think. But I'll think about that in the next video maybe, or in the future video. So we'll do some, yeah, we'll train it. We'll train the model. We'll train the model here, right? So yeah, we'll train the model here, and then after that, after training the model, we'll save it, and then yeah, we can just use this model to predict on some, let's say, test images, and then after that, after yeah, this is the main function to do object detection. We'll do some image pre-processing. We'll divide that by 255 to normalize this like the vector, the output vector or the image, right? And then we're going to reshape it, and then we're going to use that to predict, and then we're going to get the coordinates. We're going to find the x max, all that, right? And then classic image pre-processing. We'll convert that into a number array. We'll get the coordinates and all that. And after that, after we get this number array, we'll actually extract this part. So let's say the model predicted that this part has, let's say, text box, and then we're going to actually extract this image and make it the whole image. So we're going to just extract that part. And then after we have extracted that part, that particular coordinates that are actually predicted by the model, we'll run that through a optical recognition model, which is actually pretty simple here. It's just a function that is already we can just use it to, right? We can just use a pre-trained optical recognition character recognition model. I think yeah. So this is the library, PyTesseract, right? So PyTesseract is a library, I believe, right? We can just use this function called image to string to actually extract the text from this image. So what we essentially did in the above section is we have built a classic neural network, a normal neural network, to actually get that particular section of the image that contains the text, and then we're going to use this like we are going to input this text, that particular text, into this image to string function that can just, I think it calls a written model, optical character recognition model, and we can just get this output. We can just print the text. So that is the little project. And so that is a little project I have done. So make sure to go through that code. If you want to make any changes, just feel free to add some commits. And yeah, thank you for watching, and I'll see you in the next video.